Welcome to the Cognitive Crucible, produced by the Information Professionals Association. Our website is information-professionals.org, where you can find links and information about today's conversation and get access to members-only content. Join John Bicknell and explore all aspects of our generational challenge, cognitive security. The Cognitive Crucible is a forum that presents different perspectives and emerging thought leadership related to the information environment. The opinions expressed by guests are their own and do not necessarily reflect the views of or endorsement by the Information Professionals Association.
My guest today on the Cognitive Crucible is Dr. Paul Lopata, who is a quantum research scientist at the Laboratory for Physical Sciences in College Park, Maryland. Previously, Paul served as the Principal Director for Quantum Science in the Office of the Undersecretary of Defense for Research and Engineering, where he focused on quantum technology modernization. He was also Executive Secretary for the Defense Science Board's Task Force on Applications of Quantum Technologies. Dr. Paul Lopata, welcome to the Cognitive Crucible.
Good morning. It's great to be here.
Before we jump into this serious national security topic related to quantum technologies, I hope you won't mind having fun for just a moment and maybe debunking a few common myths about quantum. It seems these days that there's a lot of quantumization going on. People tend to bolt quantum onto concepts and capabilities, or even apply the word quantum to help explain things that are mysterious. Do you have any favorite examples of this kind of thing in popular culture or otherwise?
Oh, sure. Yeah, it shows up a lot. There's a James Bond movie called The Quantum of Solace. We've got Quantum Leap, a show that I used to watch in my parents' living room growing up.
Mm-hmm.
My favorite example is when quantum gets stuck on products that have nothing to do with quantum physics. So there's a famous brand of dishwashing detergent here in the U.S. that has various qualities at the grocery store, and the best quality you can buy, the most expensive, is the quantum version. And so I tried it. It's actually pretty good. I use it from time to time when it's on sale, but it's kind of like a word turbo used to be for products. They tack it on when they want to give a sense of quality and maybe technology.
Right. Well, it's quantum, right? I mean, that's awesome. So it must really do something special to those dishes.
Yeah, that's right. They come out clean and shiny every time.
Yeah, and it's a mystery how it works. We're not quite sure how it works, but it works, and it has something to do with physics. Yeah. Okay. Awesome. Well, with that, just like a little bit of levity behind us, could you just give a beat on how you perceive our national security climate right now?
Oh, sure. That's a big question, and maybe I'm not the right person to speak on it broadly. Touchstones for me are things like the National Defense Strategy and other things that come out. But when I think about national security, I'm often, because of my background, because of where I work, thinking about it from the research and engineering perspective, and looking at how we're, as a nation, developing technology and learning how to use technology better for national security and national defense. And my recent opportunity working at the Pentagon for the Undersecretary was a great opportunity. I worked with some terrific, hardworking, and amazing colleagues, and there really is a focus on making sure that our military is developing the latest technology and understanding how it's going to be used for things like advanced warfighting concepts. So it's a pretty exciting time.
Right. Well, quantum science, I think, for 99.999, you can run those nines out for a while, is something that most people don't understand. So how do you typically introduce quantum concepts to a lay audience like our audience here?
Oh, sure. So, as you say, folks often don't run into quantum science even in college. Oftentimes it's something that shows up for a physics degree in the senior year of college, right before graduation. And there is a lot of advanced stuff there. But what we're seeing is that a number of these things are having an impact on day to day, and there is more interest in it. And some of these ideas are percolating around in ways that are pretty neat. So when I talk about quantum science, it's, I often introduce it as a theory that was developed in the early 20th century to address several open scientific questions. Things like how light interacts with matter, how matter builds up everything around us out of atoms, and why materials have the properties they have, why metals behave like metals, and why ceramics behave like ceramics, and other things like that. And so the underlying theory of quantum science, often called quantum theory, puts forward this idea that the material universe exhibits both particle and wave properties, and that this is at the smallest level, and that these dual properties of particles and waves also exhibit this random probabilistic behavior at the smallest level, and that when we try to resolve these features and try to get our heads around them, that we're sort of stuck with the fact that there is this uncertainty and that there is this probability that happens at this really, really small level. And this theory has been really fantastic at explaining things like, why lasers work, why semiconductors behave the way they do, and that we can build microchips and things like this, and that how we build these complex systems out of these very simple elements. And some of the things that are involved in quantum theory get kind of strange. There's a story about Isaac Newton when he developed his rigid laws of motion, talked about gravity, and talked about how the planets revolve around the sun and move very elegantly. At the time, in the Age of Enlightenment, people talked a great deal about God as clockmaker. He set things in motion and they all just moved very smoothly, and that we can then calculate and tell where the moons of Jupiter were going to be years in advance, and that was just sort of set in place, and that everything moved elegantly. Now, when quantum theory came along at the beginning of the 20th century, it really threw these ideas on its head. Folks like Einstein and Schrodinger and Heisenberg, they tipped this worldview and said, things are predictable, but only to a certain extent. That we now have these probabilities involved, and that that it was often difficult to get these two views of the world to mesh, and even Einstein struggled with it, and he famously has a quote that says, God does not play dice, sort of struggling against the theory. And so with quantum theory, you in some ways throw out this idea of God as clockmaker. You now have God as gambler, which is totally heretical. But there it's very interesting, because starting in the 1980s and 1990s, computer scientists started speculating that some of these strange properties of quantum mechanics that otherwise were just understood by folks who were trying to explain the world around them. They said, well, what if we use these strange properties of quantum mechanics to try to build new things that we can't do otherwise? And new types of computers that are called quantum computers, new schemes of communication and encryption called quantum key distribution, improved sensors that people call quantum sensors, and that how these applications and the excitement around them have led to where we are today, this sort of revolution of quantum technologies, and how that is really not just changing how folks are looking at things scientifically, but looking at them in a practical way that we anticipate having an effect on the civil society and how the military does things.
Wow. Yeah. Thanks for that intro. That's awesome. I hope you don't mind if I ask you a couple of follow-up kind of curiosity questions.
Sure.
So I mean, you mentioned that quantum has, you can tie it back to early 20th century
Mhm.
physics. But yeah, before that even, is there some kind of an anchoring point in philosophic traditions? Like in my clumsy way of describing this here, there's like inductive reasoning and deductive reasoning, or coming to understand the world by just thinking about it. I think that's like the kinds of things that Descartes did. But then there's making observations and coming to understand the world by empirical observation. What's your comment on all of that kind of thing? Where does quantum map back to?
Oh, and for quantum physics, it's very much something we've been forced into by observation.
Hmm.
I don't think anybody would have come up with quantum theory without somebody, without all these observations, all these things in the physical world that didn't match what we call classical theory that came before it.
Hmm.
That the classical theory of gravity described the planets and how things move extremely well. The atomic theory describes that there's elements that make up the world, and that you can describe materials and what's around us by combining these elements. Optical theory describes light really well, and we saw Maxwell's equations from the 19th century that really nailed that down. But then at the interface of these things, when you're looking at how light interacts with matter, one thing that people saw was that take neon lights, right? You see them in Las Vegas, or at least old Las Vegas, you'd see neon
Okay.
lights, right?
Yeah. Yeah.
Signs and things like this. So these tubes filled with a gas that you electrify them, and you see these beautiful colors. And so if you put those colors through a prism, you see that those colors aren't a continuous spectrum, that there's specific lines of colors there.
Hmm.
And then depending on what gas you use, if you use mercury, you get different colors. If you use helium, you get different colors, and the lines that you see show up in different patterns. And they're very consistent. If you use the same atoms, you always see the same pattern of lines. And explaining this, which scientists call spectroscopy, explaining how these patterns develop and why they're there and why they're different for different elements was a total mystery. Nobody could explain it. And it required quantum theory and these strange ideas underneath it, with probabilities and the fact that electrons can, they orbit the nuclei, but only have certain orbits that are allowed. That they can't be anywhere. They can only be in certain places and not others. And that
Mm-hmm.
requires them, to jump from one orbit to another to get there. And by jumping, they either absorb light or release light. And so these, and by the way, that's where you get the term quantum leap from, is this electron jumping from one orbit to another.
There we go. Just like
nothing,
just like the TV show, right? Yeah.
That's right. Just like the TV show. So the when it comes to the philosophy behind it, it was very much rooted in observation of the world and being able to explain these observations with existing theories, or not being able to explain these observations with existing theories, and having to invent new theories to say, okay, in order to be consistent with what we see around us in the world, here's the new theory. And what's been amazing about it is these theories have been able to predict subsequent things that sometimes were surprising, sometimes were hard to measure, but those subsequent predictions have all held. And these subsequent predictions that quantum theory says, if you do this new experiment, it's going to show this result, that has continued to hold since the theory was developed in the early 20th century. And so that is what gives us confidence that quantum theory is a way that we can describe the world around us. And it also gives us confidence that if we're going to be inventing these new things, whether they're quantum computers or quantum communication or quantum sensors, we're going to be inventing these new things that rely on that theory, that we expect them to hold true as well.
Right. There's that famous double-slit
Yep.
experiment. Was the double-slit experiment the first learnings about there's something going on? Maybe you could describe that real quick. I put myself back into the mind of, I'm sorry, I don't know who the first people were who were conducting that experiment, but that must have just befuddled them for years when they were observing this. Do you think you could take a beat and try to describe that experiment?
Yeah, absolutely. And the double slit experiment is something that was originally done with light, and that if you take a bright light and then you stick it in a box, and out of that box you just have two series of cards. So out of the box you just have a little say pinhole to let light out of the box, and then between a pinhole and a screen where you're gonna present where you're gonna show that light, the light is gonna shine onto that screen. As you might imagine, if you just put a screen from the pinhole, that you'd probably see a circle as the light spread out from the pinhole, and if you had the screen, say a few feet or a meter, depending on how you like to measure, away from that hole in the box. Now, if you're doing this in a dark room, it'll be easy to see. Now, if you take a big board that just has two vertical slits cut into the board, very thin, and you put that between the pinhole and the screen, then the light, to get to the screen, needs to travel through one of the slits or through the other of the slits. And because we understand that light has wave-like properties, that you'll end up seeing a pattern of light and dark fringes on the screen. And because the light that's coming through one slit and the light that's going through the other slit interfere with each other to make a pattern on the screen. And it's well understood because of the wave-like properties of light. Indeed, when I was in high school, we did similar things like this with water tables, and just looking at physical waves interfering and to understand this. Now, one of the curiosities about matter is that if you do this same experiment with electrons, and instead of using a light source and light going through this whole thing, if you do this with something that is physical, like an electron or like a neutron, which is something that makes up the nuclei of atoms, is that you can actually design a similar double slit experiment and send out electrons that do this. And if you send them out one by one, then you could imagine that as they're going through this experiment, they might be blocked somewhere along the way. But if they do reach the screen, then you could have a screen that's covered with, say, some glowing material that'll glow when the electron gets there, and it'll make a little bright spot. And you can do this experiment with electrons, and it'll actually show the same behavior as this wave-like behavior as light does. And you can actually build up this image on the screen one by one. So if you collect electrons at the screen, and any one electron will just land somewhere, and then you do it again with another electron, it'll land somewhere else. But it'll turn out it'll never land where the dark fringes are. It'll only land where the light fringes are. And if you do it over time and collect it, over minutes or hours, then you'll once again build up this series of fringes. What's tricky about it, is if you think through it, you say, okay, well, it comes out of the pinhole, and then it goes through one of the slits or goes through the other slit, and then you say, okay, well, if it's just going through one slit or the other, then you wouldn't expect this fringe pattern. if it behaved like a particle. But for it to develop this fringe pattern, there must be some wave-like behavior here. There must be this interference, and you imagine that once again it's difficult to imagine this, but the experiment shows that the path that the electron takes from one end to the other has an influence on where it goes, and so the fact that that both slits are there, and that oftentimes they say, oh, the electron behaves like a wave and goes through both slits, and I'm making air quotes that you can't see, but it's difficult to imagine this. But what quantum theory does is it provides a way to predict where the electron will go. To say, if you set up the experiment like this, and we start it like this, we can predict the outcomes. It doesn't necessarily give you a warm, fuzzy feeling inside to say, okay, here's what the electron really is, because you're still left with this vague uncertainty of really what happened. Like, we would expect it to go through one or the other, but the theory itself makes predictions like this, and these experiments tend to repeat what the theory predicts, which continues to be amazing. And this experiment that I don't know if I'm doing a terrific job explaining it.
No, it's good. It's good. Yeah.
The Richard Feynman, Nobel Prize winning physicist, from grew up in New York and spent later life in California, and was one of the youngest members working on the Manhattan Project. He described this double slit experiment as like the explanatory experiment in quantum physics, and he's written widely about it, and really said that it really gets to the heart of some of the strangeness of this theory, and some of the new properties that come out of this theory that you'd never expect just with conventional physics.
Right. No, thanks for that. And also, coming out of this, isn't there something that's known as the observer effect, where the attempt to actually observe what's happening appears to affect the observation? Did I get that about right?
Yep, you did. Yeah. So quantum theory, has this dualness to it in many different ways, and one way that it shows up has to do with how the system behaves if it's sort of evolving in a sort of isolated way, and how it behaves when it's interacting with much more complex things in the rest of the world. Because one thing that we know is that we don't see these effects in the everyday life. And so,
right, this is at the atomic scale, right?
Right. This is at the atomic scale. This is when things get extremely small. This is what you see when things get extremely cold, close to absolute zero, things like this. And so, we're not expecting to see these things in everyday life, but there needs to be this connection between what's happening at the atomic scale and what happens when you're in everyday life. And this is described through the theory as a sort of measurement event. And if we think about this double slit experiment as the electron gets emitted from let's say a hot wire inside this box, and it gets emitted out of the hole and then travels along its way to the screen, that pretty much everywhere from the very beginning of where it gets ejected all the way until it hits the screen, we're going to be describing it in one way. But then it'll be sort of a very natural evolution where many things are possible. But then once we talk about it hitting the screen, we say, okay, it makes up its mind. If an electron can be said to have a mind, and it hits the screen and it shows up someplace. And this event is drastically different than how we describe its natural evolution in in the middle part. And so this observer, which in this case is a screen and somebody looking at it, or some other extremely complex system that interacts with it that breaks this sort of elegant evolution that happens in the middle, that this observer effect is where the probabilities happen. Is saying, all right, we don't know what's going to occur here. We don't know which of these bright lines it's going to show up on, but we know that it's going to show up on a bright line instead of a dark line, because that's what the theory predicts. That's what makes them a bright line instead of a dark line. And that that once that happens, then essentially the experiment's done and we have to start over. And so that by interrogating the system, by doing something that's drastically different to the system, by in some ways knocking it out of its quantum evolution and forcing it to interact with the rest of the world, this is sometimes described as the measurement problem, sometimes described as observer, and in many ways there's a difficulty of language when it comes to describing quantum theory in sort of everyday words, because when you fall back on the mathematics and describe things, there's a certain preciseness to it. But then when you sort of extract it to everyday language, then it sort of becomes a little funny. I even slipped in if the electron has a mind, right? Which very few people argue that it does.
Right. Well, it's hard to convert these principles or these theories into words, for sure. This is more of a comment than it is a question. When I was a kid, I can remember really vividly being frustrated with what at the time to me seemed to be like really silly philosophical questions. Like, I cannot believe people spend their time thinking about this kind of stuff. And the one that really comes to mind for me is the old saying, if a tree falls in the woods, but there's no one there to hear it, does it make a sound? And I thought, that is the dumbest thing I've ever heard. I mean, come on. But in the context of this conversation, I don't think that the philosophers back whenever they posed that question were thinking quantum, but actually it makes a lot of sense in the context of this conversation. Do you know what I mean?
Yeah, no, I hear you. And it's interesting because in my career I've had the opportunity to interact with some pretty amazing philosophers of science who really do think deeply about these questions of the nature of science and the nature of knowledge and these sorts of things. And there's this really interesting interface here for folks who are interested in it.
Right. And I also think this always frustrates my wife. She says I just go on and on about stuff. And so this is an example of that. Even after I say, this is the last thing I'm going to say, it's not always the case. But I'm also reminded of inflection points where on one side of the inflection point, there's a certain set of rules, but then somewhere along the way, those rules just kind of don't really work as well, and there's a different set of rules. And I'm thinking like, like personal finances, right? The way you manage your own personal budget and your own bank accounts and all that kind of stuff. The way people think about that personally is very different than the way governments think about that. And I mean, there's all kinds. You can have all kinds of arguments about that, but there's something to that, right? Governmental budgeting is just a different thing than personal budgeting, and there's different rules and there's different efficiencies. And somewhere along the line, there's an inflection point, right? And it seems kind of like that as well at the atomic scale. There's these things that are observable, but somewhere along the line there, those rules get drowned out or something by the rest of the real world. Do you think that there's something to all that?
Absolutely, yeah. I mean, and that is, that is the crux of the matter. And when folks are looking at these new quantum technologies that employ these very interesting effects that you see at this atomic scale, that is part of the major efforts that are undertaken is to push the push the length of time, push the amount of fidelity that these quantum effects can show. And so, I think we'll probably talk a little bit later about quantum computing, and that one of the major efforts that's done there is how to keep a quantum computer running for a long time without letting the rest of the world creep in, and forcing it to either make an error or have one of these measurement events, and how to keep the term of art that's often used is quantum coherence, and this to describe how the system stays in this elegant evolution for the longest time possible.
Right. Yeah. All right. Well, thanks for that intro. That I let my own curiosity carry that on a little bit longer than I thought. But let's try to connect this up with cognitive security, if we may, Paul. So the way I think about cognitive security is in operations in the information environment is that ultimately it's about affecting decision making, and it could be affecting the decision making of a single person or a targeted group of people or whole societies. But information operations and influencing people is as old as people have been interacting with themselves. But today we have different ways or avenues of delivering information to affect decision making, and that's really this whole project is figuring out ways to manage cognitive security. Do you have any way of connecting quantum with cognitive security?
Sure. I see two ways in which there's a connection, and one of which that I think we've talked about at length so already is these ideas that we see in quantum theory about understanding the world around us, and how it's manifests itself, and how we rely upon experiment. There's a large probabilistic effect in quantum theory, where in real life, when we learn things, that sometimes we fully trust it, sometimes we partially trust it, and have to decide what we're going to do based upon limited information. And so there's this whole sort of building decisions and designing things based upon limited information, based upon probabilistic information. And I think that's something that folks are forced into when using quantum theory. And I think it's something that folks who are sophisticated users of limited information do a lot of as well. And so whether it's making decision making around risk, whether it's risk of fires, or risk of danger, or whatever the risk is, there's limited information about what's going to happen, and you have to reason about it. And there's a lot of that reasoning that happens in quantum theory and in the technologies that happen with it. And then there's a second piece of it that I think is very concrete, and it's going to be growing over time. And some people are focused on it now, and I think more are going to be focused on it in the future. And this has to do with an advanced quantum technology called quantum computing, and its impact on the future of cryptography. And when we talk about cognitive security, when we talk about reasoning in the information space, there's certain things when it comes to information exchange that we need to rely on. that if we're sharing bank information, that we want to be very confident that the bank is only listening to us when we're saying to deposit or withdraw, and not somebody else. And when we're sharing other private information that over the internet or over the phone, so we want to make sure that others aren't eavesdropping or listening in. And we often use cryptography to protect this information. And there's a major effort underway right now by NIST, the National Institute of Science and Technology, to develop new standards of cryptography, because there's a worry that quantum computing, as it advances and as it develops, is going to be threatening existing standards of cryptography. And so there's this great effort happening, and I believe NIST just entered their third phase of the competition. Phase might be the wrong term, but it's certainly well underway of choosing on these new standards. And one of the major motivators there is to address this possible threat by quantum computers.
Yeah, thanks, Paul. Coincidentally, I'd like to refer our audience back to a discussion that we had a couple of weeks ago with Elham Tabasi of NIST, where she talks about how standards are important in a national security context. And you were just referencing another project with NIST. I don't believe that came up in our conversation, but I wanted to ask you a follow-up about quantum computing. So my understanding is, and with cryptography, my understanding that with cryptography, prime numbers play a critical role in cryptography. Could you take a beat on that? And also, my understanding is that one of the things that people are hypothesizing is that quantum computing is going to be so powerful that it's able to tackle some of the hard mathematical problems that people haven't been able to figure out with regular computing. Like it's called something like NP hard. Anyway, could you just take that in whatever direction you think is productive?
Yeah, sure. So quantum computers are these machines that intrinsically utilize these quantum science principles to perform, in principle, certain calculations faster than we can do on any conventional machine. And one of the early results from the mid 1990s by a fellow named Peter Shor was about factoring prime numbers. And it said if you can build a quantum computer that's big enough and works with sufficient capability, then it would be able to factor prime numbers faster than any other machine could. And what made that quite significant is our cryptographic standards that we just talked about. NIST publishes these standards, and so that everybody can use them. One of the standards, RSA, relies upon the fact that factoring prime numbers is a very hard problem to do computationally. So, if you take the number 21, right, it equals 3 times 7, and those are the prime factors of 21. But, if the number gets really, really, really big, like, is, hundreds of digits long, then, getting your computer to solve how many prime factors it has is a really, really difficult problem. Mm-hmm. And so it's totally amazing that these quantum computers that are designed with very different principles than conventional computers would work at all at even solving any problems, but two, that if they work well, that they could solve some problems much better than any other conventional machine. So you mentioned a class of problems that folks talk about, NP or NP hard or this sort of thing. And the fact is we don't know yet what class of problems quantum computers are best at. We have a number of examples that quantum computers are better at than the best thing that we can do conventionally. Factoring prime numbers is the classic example of this. There's other things like Grover's algorithm that can search through structured databases that can do things faster. And there's a handful of other problems that we have. And one of the big things that's happening right now is a major search as to figuring out which problems can be solved using the machines at the same time as people are working to develop these machines, because the computer science is pretty clear that this is a new class of computers, and they'll be able to solve things very differently. And the fact that result came out, through all this abstract work in the 80s and 90s, and then quickly people doing an awful lot of experiments to try to make these real, that continues today, is it really is an amazing intellectual accomplishment. And understanding that is out there, and that they can have a very practical effect on cryptographic standards of today is sort of makes it an even more pressing problem to understand. And so as we're looking at the how to mitigate this threat, it really is built on developing and standardizing these new codes that NIST is stepped ahead on and is leading the way in that standardization.
Right. So to make this concrete, the big blinking red light of worry right now is someone with nefarious purposes developing the way to breach these cryptographies using quantum technology, right? And if that happens, then our world and our society is already vulnerable, but this would just open up a whole new dimension of vulnerability, which is just worrisome to even cogitate on. Is that about right?
Yeah, every time your browser has a little lock up in the HTML bar, or what is it, URL bar, that that means that the connection is encrypted. And we rely upon this for things in civil society. We rely on encryption to protect government information, and this is a big deal. Now, to be clear, existing hardware is a long way away from demonstrating this. Current best-in-class machines, that are measured, in this unit called qubits, best-in-class machine that is 150 qubits or less. Estimates in the academic literature suggest that tens of millions or hundreds of millions or billions of qubits are needed for a machine to threaten existing cryptographic standards. But there's a lot of money being devoted to developing applications, to utilizing the machines for practical things like designing new materials, for understanding chemistry. There's a lot of good and interesting things we hope to be able to do with these machines when they're developed. But there is that threat. And so, the mitigation is updating codes to these new cryptographic standards. And, it's, really understanding that and tracking that and, following the progress, really points towards a need for understanding that and getting things implemented well before these threatening machines show up.
So many, or like everything, all technological developments have two sides of the same coin, where it can be used for great good or for evil.
Alfred Nobel, invented dynamite, right? And so that's my understanding is that's how he made his money. And I think he made a lot of money from the mining community, where folks could more easily access underground materials, but also made a lot of money from militaries who deployed them for great effect. And I think part of him looking at his prizes and looking at the Peace Prize and the scientific prizes was ways to understand, hey, how do we, maintain our levelness, and how do we maintain our even keel by promoting these better parts of our angels. Or I screwed that one
Right.
up, but promoting our better angels, right?
I get what you're saying. It's all part of the crooked timber of humanity, the Nobel Peace Prize, and here it is. You're citing that he invented dynamite. It's funny. Here we are concerned about these cryptographies getting broken at scale, and you say that that's a ways off. Sure. I'm wondering if there's probably going to be some new things developed which are maybe completely different kinds of ways of securing applications. Like here's something else that the Department of Defense like put out there as a request for information or as seeking ideas, and it's kind of like a Back to the Future kind of a thing where trying to revive old technologies in order to circumvent these kinds of technological problems that we're having today. And the one that comes to mind for me is celestial navigation. So the deal is that we're so reliant on satellite communications and GPS whatnot for our navigation today, and that's a glorious thing. It's fantastic, but it's also vulnerable to hacking and just getting brought down by some kind of a clever way of taking down the network. And then what? We're in a bind. So the idea is, well, the enemies of the West are probably not going to hack the stars. So how about let's develop some clever AI techniques that are kind of back to the future and use celestial navigation when possible, and that way it's less likely to get brought down in some kind of a catastrophic event. So I'm curious if you or your colleagues have ever kind of armchaired, sat around and thought about other ways to secure systems other than the password methodology that we use today, which is at risk, as we were just describing with quantum technologies.
Sure. So, I think that's a great example. And I've even heard that, the, the use of sextants and things like this at the Naval Academy, after waning for a while, have come back to into the course of study.
That they are coming back in?
That's what I've heard. Yeah.
Is that right?
Yeah.
So I was in Naval ROTC too, and we took a class on celestial navigation, and that was one of those classes at the time where I was like, "You've got to be kidding me! What are we doing here?" But anyway, here we are 30 years later, and it's a legitimate, serious conversation. So okay, proceed.
Yeah. And I think there's a lot of different ways that people are thinking creatively about passwords, about protecting information, and really thinking about it. For me, from a risk perspective, is often a way to to appreciate a problem. And if you look at very unlikely events that might be catastrophic, like if something goes wrong with the whole GPS system, how does one get around? How does one distribute time, which is also another thing the GPS system uses.
Oh, right, the atomic clocks. Yeah.
Yeah, and so and that's a whole different conversation that I'm happy to chat another day. But there's some great work that's done at the U.S. Naval Observatory and places like the Office of Naval Research, developing atomic clocks and making sure that they're available for folks who need them. But I think a lot of those things. I love things that are simple, and I love things that can be implemented in ways that aren't necessarily high tech. So I think the more folks try to think about these things, even if they're backups and even if they're, a secondary system, it can be very helpful, because at the end of the day, they might be useful enough to be a primary system that is resilient and can satisfy a number of things, even if it isn't so new and shiny.
Right. Well, humans are really good at solving problems, and so if a problem becomes vivid enough, some kind of a solution will emerge. Okay, so this is one of those questions that I like to ask people. So if you had 2 minutes with the President of the United States, or some other really influential person, and you wanted to pass along to them just a couple of things about quantum, where we are, where we're going, what are those things that you would like to leave this kind of person with?
Sure. I think that the precedent in this area is in good shape, because we have a national quantum coordination office under the Office of Science and Technology Policy that is focused on this issue, and is really looking to make sure that where we're going as a nation is in the right direction. And there's a report that I had the opportunity to help contribute to, that came out a few years ago. Talks about a national strategic overview for quantum information science, and it focused on 7 different important areas for this, and I think some of which we've already talked about, but one of which is just the science, and how this is still in many ways early days, and so we need to continue to fund scientific work in this area. There's a workforce element where more people are getting excited about this, and we're needing more and more folks to get involved. And so if you do a search online, you'll see that many different companies are hiring folks like crazy in this area. There's an infrastructure piece where new equipment and new connections are made between people to allow these things to happen. Industry plays a strong role, because while academia and the government are doing some neat things, that we're looking at industry growth, and we're looking at their connection to the overall effort of the country. There's an economic and national security piece to it, some of which we've talked about already, especially in having to do with cryptography. And there's an international cooperation piece, where not only is there opportunity for academic exchange, but also government exchange with sharing where we're going and what we understand, and working together. So I think focusing on those things in this broad area is important. And I think for the topic that we've discussed is really looking at the this connection to ensuring that cryptographic protocols are safe going forward, and that they're getting implemented is going to be a key for for cognitive security, for cybersecurity, and just our national security.
All right. Well, thanks for that. Could you leave our audience with a good book, or something that if somebody wants to take a little deeper dive into this, or something related that you've appreciated?
I'm going to give you a couple quirky books here. For a while there, I got a kick of reading a number of books on Antarctic exploration, and there was a book called The Worst Journey in the World that talked about the race to the South Pole. And one of the things they talked about in there was just this, the use of celestial navigation and understanding where folks were on the continent, and where they were going. And so that's a neat book. And one book that
What's the title of that book?
Oh,
please?
It's called The Worst Journey in the World.
Gotcha. Okay.
And then another one that I read recently that I got out of the Pentagon Library was called Lincoln in the Telegraph Office. And for me, that was fascinating, because it was a memoir by a telegraph operator during the Civil War, which was in the building next to the White House in the War Department. And talked about how the Army stood up this telegraph capability so they would have it during the war, and that how Lincoln would often go over and be in the telegraph office in order to get the dispatches right when they came off. So there were some, fairly low-ranking folks in the telegraph office who were, standing up to give their desk to the president so that, he would have some place to sit down and work while he was waiting. And, it was pretty fascinating because there were, issues related to codes there. These guys turned out to be some pretty good code breakers. If people found some codes that they couldn't break, they'd bring them to these guys. Talked about, communication at that age and really talked about how this new technology got rapidly implemented into a major war effort in very little time. So I found that book pretty fascinating.
All right. Well, thank you so much for those suggestions. We'll have links to all these resources that we mentioned in the show notes. I think I'll also drop a couple of YouTube videos into the show notes that are like short little explainer videos on quantum related stuff, and also that Shor's algorithm too. But anyway, with that, Dr. Paul Lopata, thank you so much for being a guest on the Cognitive Crucible.
Oh, you're welcome. I'm glad to be here, and thanks for the opportunity.
The Cognitive Crucible is the only podcast dedicated to increasing interdisciplinary collaboration between information operations practitioners, scholars, and policymakers. To find out more about the Information Professionals Association, visit us at information-professionals.org. Please support our podcast by giving us a 5-star rating and leaving a review.